In today's next video, we'll be exploring Rosalind's next problem. That we're going to be doing is Mendel's first law. And click this drop down and provide sort of the context regarding Mendel's first law, Mendelian inheritance. Provide some context about Punnett squares, and if you have these sort of characteristics, then in terms of as it gets passed down to generations, there's sort of this likelihood of having this sort of two possible alleles. And in terms of the problem statement, general summary is that it primarily deals with probability, dealing with sort of these random variables, more information defined under this general diagram tree. And then, yep, gives you this problem statement that we will explore. And then ideally, we need to return this sort of case right here where an individual is possessing a dominant allele. All right, three positive integers k, m, n, representing a population containing organisms, blah, blah, blah. You need to return the sort of probability the individual will have a dominant allele. So in this case, we could say, but let sort of D represent the recessive allele, and let capital D represent the sort of dominant allele. And so you can technically say, hey, this technically works, this technically works, right? And then this technically works, vice versa. But generally, we want this sort of characteristics, right? This would not be included in sort of the likelihood or probability because those are both homozygous recessive, at least in the given offspring. And this is sort of the decision tree that was provided. And important to note that ultimately these values actually add up to 1, right? 3 out of 10, 3 out of 10, 3 out of 10, 1 out of 10 adds up to 1 in total. That's what we need to consider. And then to further break down this sort of problem, this is sort of actually, I would say, a two-step problem. First case is we need to sort of understand the probability of two individuals sort of mating, right? So two individuals mating. And then the next probability that we need is from those two individuals that were mating, we need to sort of establish the likelihood of the offspring having this sort of dominant allele, right? That was represented above here. And then we can actually, move down further, sort of explore this particular case, knowing what we know now. We could say 2, this example, 2, k, m, n. We could say let k represent what we know is this is homozygous dominant. And using our sort of representations, this is heterozygous dominant, and this is homozygous recessive. And I think for the sake of this working example, we can actually, turn this into a smaller sample size or whatever the case may be. It doesn't really matter. But what we know, the population size is actually population size equals 6, right? This is this. And from here, we can sort of say, hey, from this mix of combinations, what are the different possibilities, right? So we have K, K, MK, and then we have K, N, right? And then from here, we then have M, M, we have M, K, we have M, N, we have N, N, we have N, M, we have N, K. And from here, thinking to yourself, technically you can argue that, N, M, both are equivalent, right? Same case for this one, M, K. You think, don't we just need all the 6? But this is not the case, right? We need every single instance because this sort of accounts for the probability. I mean, in theory, at least these are technically the same. This one and this one, this one, this one, likelihood of probability. But in terms of the sum of the probabilities, given this sort of random event, this needs to be accounted for, right? Because these are completely different events. We can explain that further on. And then, yeah, so these are the individuals mating. and then we need the likelihood of the offspring. So from this one, we can just sort of leverage this functionality here, or not functionality, or this decision tree. Let's say you have this individual with this sort of homozygous dominance, and then we have another individual that has this sort of properties. And then next, for the likelihood of the offspring, we just simply need to, leverage Punnett squares, for example, like this, to sort of establish, the likelihood of that offspring having this said dominant allele. Okay, doing some calculations offline and working off the sort of necessary steps that's needed to establish the sample output. These are sort of the described characteristics of what is needed from my end, right? And this is sort of the list of combinations. And as mentioned, these needs to be treated as sort of individual events, despite having equivalent or being equivalent. And then as I work down the tree, and then this will be linked in the description for the resource that was used to sort of have a tree diagram that was, similar to what was initially provided. I realized that as you navigate down each tree, it results in sort of a much more complex sort of calculations and having to add, each steps. And then for my case, instead, I realized that instead of having to sort of find cases where, you find said dominant alleles, like this case, and for example, I decided that instead, it'd be much easier and much more refined to find cases where there would be sort of this particular case, right? Where you have an offspring that is homozygous recessive. And from here, I found that this is a case, this is another case, and these two are cases where there could be a likelihood of a dominant or homozygous recessive offspring given this sort of mating individuals. And this matrix is sort of representative of having a dominant allele, and this is sort of representative of having a homozygous recessive combination. And then sort of essentially, let's walk down. I calculated sort of the probability and sort of represented by the tree as you sort of navigate down, right? So in this case, probability 1 of having that likelihood, 1 in 4 chance, MP 1, right? And ultimately, the sort of probability of each event, right, as derived from just going down the tree, this will equate to having a probability of having an offspring that will be homozygous recessive. And then you take the complement, and this is sort of the basic understanding of what a complementary event is. And then from here, this should result in the probability of a offspring having a dominant allele. It could either be this combination, but just to briefly walk through in terms of how this is being explained, essentially, for example, let's take case 1. I essentially navigated down this path, which would be case 1, and navigated down this path as a start, and then realize, okay, we're going down sort of this horizontal path, so I'm going down this decision from this decision tree, and as denoted by the sample statement or diagram, it needs to be multiplied, right? So this case m over p, which is population, n minus 1, since considering that we already drawn a sample from n, and then reduce the total size of the population, and then we would need to multiply the probability of an offspring having a homozygous recessive. And then to just briefly walk through, this equates sort of the general example of the probability in using a calculator available online. And then if you take this one, 1 minus 0.2167, this should equate to its sort of the value that we expect from the sample output, right? All right, let's hop right into the coding solution. This is the sample output that I am sort of having here as a comment, as a reminder that was provided from the initial problem statement. This is the sample output. These are the list of formulas that are needed to sort of output that and then take the complement of these all together added up. And one thing I'd like to note down is that, of course, any language can apply to solve this particular problem, whichever you prefer. You can use any sort of text editor or IDEs. In this case, I'm using replit.com. And then to get right into it, first thing is I typically do is sort of denote specific things that needs to be addressed, or at least what needs to be accomplished in this given problem, right? First thing is we need to define a function, which sort of whole goal is to calculate this probability of the dominant allele as long as you just pass in the particular variables that are needed. And then you just next is then you can just then call this function and print it however you'd like it, printing it after the function is done, returning nothing, or you can just return a value, whichever is preferred. But let's just say call the function. Okay, so as provided by the problem, you have k m n equals 2, 2, 2. And then let's just say, you know what, we're gonna print out these final output based on the final function call. So allele prob, and then in our case, one thing that is important to note is that you'll notice that in the formula that is being derived, we technically don't need this particular variable, but we do need, variable in the formula itself, but we do need this to be part of the population size. So let's go ahead and say, you know what, pass in m, n, and then we just need to sort of pass in the population size into the function itself. Then now we're going to define a function, probability, and then here, typically instead of using mn, whatever, let's just make a more defined sort of variables, right? I think definitely that's sort of recommended practice, I'd say. But for the sake of this video purposes, let's just go ahead and just do n population. And here you want to say now we define all these population. We just technically just apply everything here, but being mindful of the parentheses is very important. So in here we have 2 heterodominant, let's say. And then one thing I'd like to point out is that sometimes when you're coding, it's definitely very important to have this sort of mindfulness of parentheses, since technically the sort of PEMDAS or whichever the case is now, it's still applicable here, right? You don't want to unintentionally do an operation that is sort of not intentional. So in this case, 1/4 times m over p, and then you want to say m minus 1, and then you want to say p minus 1, right? And the next one is then 2 homo recessive equals 1/4, and then we can just say, hey, just copy this. Technically, it's the same formula. You say n minus 1, n minus 1, p minus 1. I believe that's correct. And then formula 3, for our sake, let's just go ahead and store it in 2 independent variables and setting it out together so that it's clearer. And then we have hetero and homo recessive, let's say 1. We can just say that, and then half times m over p times m over p, and then n over p minus 1. And then just to be on the safe side, let's go ahead and define this. And before you forget writing functions, we need to add this sort of colon here. And then, let's see here, this one, be on the safe side. And then, let's see, hetero and homo recessive 2 equals half. It's the same formula. Now we just have n, and then m, population minus 1, and then hopefully it returns the expected output that we want, right? Add it up together, and now here we're taking the complement, and let's hope that it returns the output that we're expecting. Perfect. Oh wait, 783. So somewhere along the way, oh, this one should not be 1/4. This one, as you recall, had the probability of having a homozygous recessive. So this one should not actually be a 1/4. It should be a 1 instead. It should be good to go. Yep, as expected. And now, with this formula, either with the back to the problem at hand, you just either can read the file or you can just sort of submit the problem, but this is how you, at least the solution that was proposed based on the formula that was derived from the conceptual solution.